Morning. Good morning. My name is Rohitha Weerasinghe. So I will be seeing you for the next few weeks at this time in here. So we are to computational methods, the CFD part. So this part of computational methods will have 5 weeks of teaching and learning. So you will have 5 lectures and 5 tutorial classes. They have been timetabled, I know. So the lectures will be, it's just similar to FEA but only for 5 weeks. So at the end you will have to submit an assignment in CFD. Assignment is on Blackboard now, so you can see it. The assignment will carry 75% of 50% of the module, which is 37.5%, and 12.5% of the module is via exam. So you will have an exam at the end. So half of that will be CFD. So the module leader is Arno, who you know already. And we start from week 12, this week, week 8, this is week 8, so we start from now and we'll finish at 12. So by December. I have seen few of you in the tutorial sessions, so the rest I will see over the week. All the tutorials are on Blackboard. Will be on Blackboard. I have prepared all the tutorials, but I have released, there are 5 tutorials, so I have released 1 and 2. So this week you will be doing tutorials 1 and 2. That is meshing and setting up and running a Lamina case. So next week we will look at the results and then start with the turbulent case. And then after about 3rd week you will be able to do your engage with your assignment rather than doing tutorials in the class. So the tutorials are meant for the 5 weeks, but you will finish them early. So you can use your time to do the assignment as well in the class. Okay. And I will be there for the 2 hours, so you can ask me questions there. And so you can email me if you have questions, or if you want to if you have problems, you can ask me in the tutorial class, or you can make an appointment and come and see me. But it's fairly straightforward. So if you follow the instructions in the tutorials are straightforward, and then the assignment is fairly straightforward as well. So if you are looking at previous year's assignment, it's slightly different from previous year. It goes along with the same, goes along the same line, but the final element that you have to produce is different. So slightly different from last year's assignment. I didn't teach last year. Kerry taught last year. I taught the year before, and Kerry taught previously. So anyway, so for today we will look at meshing. So you know about meshing from your FEA, but meshing in CFD is slightly different. The same concepts, but you will have to consider few more things as well. And luckily we are using the same platform as in FEA. You used the ANSYS platform, so you used ANSYS FEA. Now here we will use ANSYS Fluent. For CFD you can use ANSYS Fluent as well as ANSYS CFX. So in this year's tutorials, in the 5th tutorial, I have included some CFX as well, but that is for completion. That is for completion's sake, because some of you may do design of fluid systems later, or some of you may want to use CFX. So in the previous years, we didn't use CFX at all in computational methods. We only used Fluent. But I have given an introduction on how to use CFX as well in the 5th tutorial. But for your assignment, it's not necessary. Okay, but it's good to learn it. It's good to know when you are here. Okay, use the time wisely. So that is an addition this year to the tutorials. Okay. So you will be applying your CFD or your knowledge that you learned from here to a laminar case and a turbulent case, and then you will be doing a laminar and a turbulent case both in your tutorial, in your assignment, but the geometry will be different. So for the tutorial you will be looking at a pipe, you are looking at a pipe flow, whereas in the assignment you will have to do a little bit more. It will be a T-junction. So once you have used the design modeler, you will know how to use design modeler to create a shape that you from basic elements. So creating a T-junction is not very difficult. So you will have lecture slides for learning materials. There are no notes. Okay, so you will use the lecture material, slides, and the tutorials. Okay, so everything that you need to know are on slides, so you don't have to print out anything else. And there are recommended reading, but the material are prepared using those recommended readings. So if you understand what we do here, that is good enough. But well, of course, when you learn, you can refer to other sources as well at your convenience. So this is where we start today. So that's my email address. So you will have it on the slide. So if you ever want to contact me, drop me a line. I will reply. And if you want to make an appointment and see me, we'll do that. I know some of you are my project students. Some of you already have met with me. So yeah. So today, so the structure for the lectures is so first lecture is to create a geometry and a mesh, the importance of that, and then in the second lecture, what we will look into the equations that are being used in the code. In code means a CFD tool. Okay, so whenever I say code, that means essentially ANSYS Fluent or ANSYS CFX. Okay. And then we will be looking at how the equations are solved in lecture 3, and then we will look at turbulence in lecture 4, and in lecture 5 we will do analysis and validation. And don't worry, I will have time for some revision as well. Okay, so even though this is these lectures say lectures 1 to 5 and that's it, that's not it. Okay, I will do some revision as well. So today we will look at meshing and theories behind meshing. So the first thing is what is a computational model? Okay, in a computational model, okay, I know when you look at CFD, you have seen graphics. Okay, what you always see are graphics. But all these graphics are based on mathematics. Okay. So a computational model is it's a mathematical representation of a real life system. Okay. And you are trying to use your mathematics or a mathematical model to emulate something. So these are two examples, a bridge and a cyclist. Well, with the cyclist, we are looking at the airflow around him, and in the bridge, we are looking at the actual structure. So you will be using two different approaches to model these. So the first one you already did. So you looked at the structure of elements. So you use FEA or finite element methods to look at the structural. To do a structural analysis on this bridge. But when you look at the cyclist or the airflow around the cyclist, you are looking at a fluid. So the behavior of fluid. Now in your structural or FEA calculations, nothing moved, right? So they were stationary. So you had forces, but they were stationary. But in computational fluid dynamics, the difference is that everything moves. Okay? It will be a fluid. So that's a basic difference. And then you have a fluid. You have something called a fluid structure interaction. Now in here, in the fan here is something like the bridge. It's a structure, and it doesn't move. Well, even if it moves, we can track its movement, but its shape doesn't change. But surrounding that is a fluid which moves. Okay. So the fluid will be resolved or solved using computational fluid dynamics, CFD, and the structure here will be solved using FEA, finite element methods. And then in fluid structure interaction, you try to couple the results of this one with the to calculate this one. Okay. So that's what is meant by fluid structure interaction. But we don't go there in this course, but you need to know the context of it. And what you use there is multiphysics. Multiphysics means it's not just fluids, not just structures, it's fluids and structures and multiphysics. So why would you use a computational model? Because there are few reasons for it. One is that you may not be able to do the same with experiments, or your experiments could be very expensive, or it is more convenient for you to use a computational model, and that can be that will be repetitive as well. You can repeat the results, or you can repeat the tests easily using computation when you use a computational model. And the alternatives, of course, are to do physical testing or physical modeling, which is very, very expensive, time-wise as well as money-wise. So last question is not that relevant, I would say. So in a computational fluid dynamics model, you will look at the fluid flow. Now, for example, the air inside this room can be modeled using computational fluid dynamics. And initially, you will look at the flow. And then you will also look at the heat transfer. So you will look at the flow, and then you look at whether the temperatures increase or temperatures decrease, or whether heat is being transferred onto the fluid. For example, if you have fluid here, when you look at the air here, air is a fluid. We can model that. We can model how it moves, if it moves within here, and then we have us heat sources. Okay, the air temperature is about 20 degrees Celsius, and your body temperature is about 40 degrees Celsius, 38, 39. Yes? So that means you will always radiate heat to the atmosphere, and then you have heat transfer. So therefore, the air surrounding you is hotter than air by the wall. And then again, the walls are cold, maybe, because the outside of the walls are much colder, maybe about 10 to 15 degrees Celsius. Therefore, the wall surfaces are not 20 degrees Celsius. They can be less than that. And there is radiation to the fluid. And we have the lights, which emit some of heat. And then we have mass transfer, in the sense we have openings, doors. So through the doors, air can move in and out. So there is mass transfer. And that is a simple case. But if you want to look at the case of a combusting air and fuel, you will have chemical reactions as well. So you have to couple all these into a CFD simulation. Okay? So it's not just looking at a flow. You will look at the flow, you will look at the heat transfer or the temperature changes, you will look at the mass transfer, and you will also look at the chemical reactions. So all these are resolved using mathematical formulae. So for the simplest, the simple formula that you can use, for example, if you had combustion, and if it is, say, methane, so you would say methane is CH4 plus O2. You can write a chemical equation. So that chemical equation, so CH4 plus O2 will give you CO2 plus H2O. So that's a chemical equation. That chemical equation is embedded in the CFD code, okay, as for combustion. In addition to U, X, Y, Z coordinates, U, V, W velocities, and the pressures, densities, etc. So results of CFD are used in new designs and in detailed product development, and also troubleshooting, as well as redesign. So these are heavily used in the aero industries. Anything related to fluids, and in the automotive industry, CFD is heavily used. Okay. When I was studying, when I learned CFD more than 20 years ago, CFD was a very, very expensive tool. In the sense, we had specialized computers that we could use for our simulations, our PCs. I started with 386s and 486. You don't even know those computers, I guess. And we could, with a lot of difficulty, I was able to run my CFD code in my home computer and the laptop. For all my work, I had to use the computers that we had in our research office. So, but nowadays you can run a CFD code in your laptop fairly easily. And for large calculations, you have clusters of computers. So, computing power, you have enough computing power these days. Well, I don't say enough, but sufficient, I would say. And with CFD, you can emulate or complement testing and experimentation as well. So, if you had seen some of your fluid experiments in your first year, some of the, well, almost all of those experiments can be modeled using CFD. So, you don't really need to go to the lab. Well, you need to go to the lab to verify it, but theoretically speaking, you don't really need to go to the lab. You can emulate everything in a computer. But there's a danger to that. Okay, don't take this for granted. You always have to verify your results. Okay. So nowadays the problem is, okay, you have the black box in the name of a computer. You put some numbers in, you get some numbers out, and you believe it. Don't do that. Because before you believe in it, verify it. Okay. But when you go to the industry, this happens a lot. Okay. You can do a nice, colorful, beautiful CFD simulation and go and go and convince your superior, and he will come with a piece of paper and do a small calculation, and he will tell you your answer is wrong. That will be embarrassing. So, for not to do that, yeah, do your back of the envelope calculations beforehand and verify your results. So go look at the basic theory and see whether the results that you get, the answers that you get, are reasonable. Okay, without doing that, don't go into a elaborated calculation. Okay. So advantages of CFD are they are relatively low cost because, for example, okay, you can buy a computer for £1,000, a good one, and you can download a CFD software for free. Okay. And then you can spend some time and do some simulations. Say, for example, for a flow in a channel flow in a pipe, or a flow in a channel, or something like that. But if you were to go and emulate that, or if you wanted to go and do a practical on it, you had to buy all the equipment, which are much more than £1,000, and you have to put in a lot of labor as well. So these, I mean, especially in here in Europe, in England, labor is fairly expensive. Okay, skilled labor is very expensive. And time-wise, you can set up an experiment fairly quickly. With if you know, you can set up a case fairly quickly. Okay, the people who did the tutorial started with the tutorial. You got some results in 2 hours, didn't you? So that's just by following some instructions. Well, had you known what was in there, it would be a real case, wouldn't it? So and also you are able to simulate real conditions using CFD. So some of which are not easy to do. For example, if you simulate combustion, doing combustion experiments is time-consuming, expensive, as well as dangerous. Okay, you have to have a certain area, trained people, etc., to do combustion experiments. So, but you can do it without much hassle using a CFD code. And there are ideal conditions which cannot be emulated using experiment, which you can do with CFD. And CFD will give you, or mathematical modeling will give you a lot of information. So you will have wanted and unwanted information. So you will have a lot of information. But when you need a piece of information, it's easy to get through using a code rather than doing an experiment. For when you do an experiment, you need to have, so for example, you need to measure velocity, you need a device to measure the velocity. Then you need to measure the temperature. You need to measure the composition. So for each element that you want to measure, you need a tool, or you need a you need a means of measuring. But when you use CFD, everything is bundled together. You can have all of them as output. So then we will look at the limitations. So we looked at we looked how hunky-dory CFD was, but now we will look at the downfalls of it. And to do a proper model, you need to have proper physical models. Meaning, if I move my hand, or if you have a flow, you must be able to mathematically describe this flow. Okay, so you did the pipe flow. So you must be able to mathematically describe it before you model it, because the flow, the CFD, or the computational fluid dynamic model, is a mathematical model. So you must be able to mathematically describe it. That means you have to have a comparable mathematical model for the physical model. Okay. And we are looking at numbers. So there can be errors. Errors are round-off errors and truncation errors. So round-off errors means your computer will store a number in CFD basically. It could be a 32-digit number or a 64-digit number. So if it is 32-bit, you say single precision. If it is 64-bit, you will say double precision. And truncation error is your approximation is finite by the size of the grid. And then you give boundary conditions to a model as well. So for your pipe flow, for example, you have a pipe, you have an inlet, you have an outlet, and a wall. Okay. At the inlet, you defined the inlet velocity to be 1 meters per second, uniform. But that's not okay. That's okay, but that's not physically exactly correct, because you can't give 1 meter per second right at the beginning of the pipe, because there is a wall, there are wall effects. So when you have wall effects, what you have is a boundary layer. So you have to define boundary conditions accurately as well. So these are some of the limitations of CFD. And the other thing is complex models can take forever to solve. Okay, so if your problem is really large, you set up the problem, you let the computer model it, and then leave it and go to sleep, and come next day it hasn't done it, come next day it hasn't done it, maybe it will take 3-4 days. Okay, so that can happen. And then you will have to validate as well. So validation is to validate results, you need to have experimental models or analytical models. So one way of validating is using pure theory and do the hand calculations and validate it, or use experiments and validate it. Okay, these are some examples. Internal flows. So this is an internal flow. That's a flow inside a pipe bend, and that's an external flow. So we are looking at the flow around this fan or the turbine. So we are not looking at the turbine, we are looking at the flow around the fan. And then what you call an open channel flow. In here, this part, this is an open channel. So the base of it is like an internal flow, but the outside is exposed to air. So it's a mix of internal and external flow. So remember, when you do a flow calculation in CFD, you only look at the fluid, not the boundaries. Well, not the container or the element that is containing the fluid. You are only looking at the shape of it. You are not looking at the material or material properties of it, apart from if there is any heat transfer. Okay. So for example, you have a pipe. Okay. If there is a pipe and there is a flow inside the pipe, you don't take the pipe thickness into account. You don't. Okay. You only look at the fluid inside, the diameter of the fluid continuum inside, the diameter of the fluid volume inside. That's what you look at, and you are modeling only that. Only the fluid. Okay. So, for example, in here, so you have a square channel and a round pipe connected to it. You look at only the fluid inside, and you don't need the duct or the pipe thickness for your calculation. So, for example, in here you need geometry of two fluid phases as well. So this is the two phases are, okay, this one is say water and the rest is air. And to do that, you in your calculations, you need to subtract your fluid volume from your solid volume. You need to subtract your fluid volume from your physical containing model. Okay. Usually, in the industry, what you get is a CAD drawing, computer-aided design drawing. But the CAD drawing that you get is not good for. You can't use it straight away for CFD modeling. For CFD modeling, you need to create your own grid, own mesh. Okay. Because to have a proper volume, that volume has to be fully bounded, in the sense. So if you take your pipe flow, you have two. You have the inlet and the outlet, so those are two phases, and your wall, cylindrical wall, and this volume has to be fully bounded. Now this cylinder has to be fully connected to the two sides. If you have any gaps, the calculation will fail. Okay. So you can have gaps between surfaces or edges. Intersecting surfaces, edges have to be joined when you take a CAD model. So you may have duplicate lines, points, etc. Now this is one of that. You don't need it. And you might have inconsistent orientation. And you may have only surfaces, not volumes. And you may have exactly the wrong shape as well when you get CAD drawings. So when you see a CAD drawing, what you take the shape from the CAD drawing, but you need to create your model, your CFD model, the volume for your CFD model using the tools in CFD, because you can't have any holes inside your mesh, okay, or voids or unnecessary pointers. And a geometry can be simplified, meaning now if you take this geometry, you have too many lines here, so you simplify your geometry first. You remove unnecessary lines. Now this process is called CAD cleaning. So you get a drawing in CAD, and you clean the CAD drawing to suit your requirement. CAD cleaning. It's not in here, that word. So this is the word that is used in the industry. And you can also look at symmetry, because if a problem is symmetric, you can only solve one half of it, and you can say it's symmetric. So your full problem is symmetric. And you can't entertain really sharp edges. So those edges you round them. And your geometry will have to have a fluid region, of course. Okay, and so for external flows, your geometry of the object is removed from the model. Okay, for external flows, and your domain must be large enough to prevent blockage or flow acceleration. So, for example, suppose you use this surface, you are modeling a car driving along a road. Okay, so if you want to not the car, the flow around the car. So for that to be a representative model, so suppose this is the car, okay, and you have airflow over it. For this to be representative, you can't just have your domain just around it. You have to have a big enough domain where you don't have any acceleration or deceleration or change of flow due to the size of the domain. Okay, so if this is a car, you have to have a fairly large domain, so that so your boundaries can be treated as infinity. Okay. So reasons for meshing. So a mesh will have an exact position in the space that you use. So the mesh will give you the exact location, okay, or vice versa. For an exact location, you have an exact grid node, and the mesh is a discrete representation of the geometry of the problem. So, for example, so you've already done this basically. So you have your fluid domain. So you slice it, slice and chop it so that you can have a mesh, and that mesh will represent your domain fully. Okay. And some of those grids are facing the boundaries. So your inlet, outlet, and your wall. Okay, so some of those cells are adjacent to the boundaries. So the effect of mesh is rate of convergence. Rate of convergence means how fast you can get a solution. So remember this: if you have a really fine mesh, that means if your mesh sizes are very small, your convergence is fast. Okay, so you don't have to run so many times for convergence. And if you have a fine grid, your accuracy is higher as well. But a fine grid means the load on the computer or the number of calculations it has to do is high. That means the finer the grid, the higher the computational or CPU time taken. Okay, so a fine grid is good, but really fine grid may not be good. For example, for simple reason that you can't accommodate that in your computer. Your computer is not big enough if you go beyond a certain limit. Okay, we'll look at some terms in meshing. Cell. Cell is the in 3D. It's the volume. It's this small brick. Okay, that's the cell. Node is a point. Okay, that is a node. That is a node. That is a node. That's a point. Cell center is that is a cell. I'm representing that in 2D here. That's the cell center. Edge is, so you know this already. That is the edge. Face is the 2D representation of it. And zone is a group of cells. Okay, so you can have, for example, the boundary. One boundary is a zone. And the domain is a group of places, group of nodes, faces or cells. It can be anything. Nodes, faces or cells. Domain is a part of that. Okay. You can say the fluid domain. If you say the fluid domain, it's everything. So cell shapes, you can have 2D triangular cells. So that's this is in 2D and this is in 3D. So in 2D you can have triangles or prisms or 2D prisms which are quadrilaterals. In 3D you can have tetrahedrons, you have hexahedrons, you have prisms with triangular base, you can have pyramids. Look at the difference between a pyramid and a tet or a tetrahedron. The base of a tetrahedron is also a triangle. Base of a pyramid is a square. Okay. And then when you go beyond that, so remember a hexahedron has 6 faces, tetrahedron has 4 faces. Okay. And then you can go as many as you want. So that is called a polyhedron. As many faces as you want, that is a polyhedron. Polyhedron. This one. And then you look at meshes, structured meshes and unstructured meshes. So in a structured mesh, when you take an edge from one side and then you go to the other side of that, you will have the same number of grid nodes. So that's a structured one. And when you take that side and that side, you will have the same number of nodes. So this is a structured grid. This is also a structured grid. Okay, this is structured, not unstructured. This is structured. If it is unstructured, you don't have the same number of grid nodes on the edges. Okay. So hexahedral meshes are structured meshes. Okay. But you can use tets for unstructured meshes. Okay. The good thing about structured is you get solutions quicker and simple to visualize, simple to understand. But with unstructured meshes, you can mesh anything, any shape. Okay. So this is the example for an unstructured mesh. So you may not have the same number of nodes here, It's not structured, it's not regular. So you can't have the IJK structure in an unstructured mesh. So these are examples of unstructured meshing. So you now this for this one you have really fine grids elements here. For what? Yeah, good. To resolve the boundary layer. Okay, you need to have a good grid resolution here. Resolution means number of grids that you have at a place. Okay, and here your grid resolution can be coarse. Now this is fine, this is coarse. Yes. So you don't, because you are not worried about the far field. So another term that is used is the near field and the far field. So near field is near the element, near the object that you are interested in. Far field is far. So as you already know, we have tri meshes, quad meshes, hex meshes, tet meshes. So tri means triangular, quad means quadrilateral, hex means hexahedron, tet means tetrahedron. And then you can have hybrid meshes as well. You can have part structured, parts unstructured, or you can have tets and hexes together if you want. And usually boundary layer meshes you would want generally hexes or prisms. And then you have what we call hex core, that is hexahedron in center and other cell types at walls. And then you have polyhedron meshes. So if you can't, yes? If you take this one, yep, you need to resolve the boundary layer here. So that means you need to have a really fine resolution there. Yes. But boundary layer, now if you are worried about the boundary layer doesn't extend beyond this point, yes? Here, no boundary layer effect. The effects or the velocities or the densities, they don't change much here. Okay? So the velocity here and velocity here are roughly the same. But if you take here, velocity here and velocity here are a lot different. So therefore, the near field means near here, you need a really fine resolution to pick up the sudden changes. Here, there are no sudden changes, so you are not worried about a fine grid resolution. So that is the answer to your question. Thank you. Okay, then you define a term called mesh density. Excuse me. So mesh density is the number of number of elements that you have. The same question basically. Number of elements that you have in an area. So you have to have a high mesh density for a refined area. You don't need the high mesh density for a coarse area. So and the implication is that you have a high mesh density. And after a certain point, certain number of cells, you don't gain anything. Now, so that is what this graph tells you. So you can have like 1.2 million nodes or 1.8 million nodes. For 1.5 million, and 1.8 doesn't give you a difference. So this is where you should stop. Okay? Definitely here, because after this it will be a straight line. So there is no point having more than that many grid nodes, that many grid cells. Yeah. So here the mesh density is too low, too low, too low. That's the right number. Not really, is it? Yeah, but so this is an example. Mesh quality. Mesh quality is a hexahedral meshes will give you more accurate solutions, and in boundary layers, usually COD, hex, and prism are preferred, because if you take a boundary layer, so now this is my car, in the boundary layer develops in that direction. So you need to have cells like that, cell layers like that, not the other way around, because you need your cell edges or the faces to be parallel to the wall. And you will look at some parameters of mesh quality: skewness, smoothness, and aspect ratio. So we'll quickly look at what they are. Skewness is how out of shape that is. Okay, that is what it means. How out of shape your cell is. Okay, this is a skewed one. This is the optimal one in this space. Okay. So if you have a really low skewness, it's good. If you have high skewness, it's bad. So skewness is defined as optimal cell size minus cell size divided by optimal cell size. So this optimal cell divided by minus that, if you have a cell just like that, your skewness becomes 0. For this one, your skewness becomes quite large. And aspect ratio is here. So now this is aspect ratio is one side divided by the other side. Okay, so you know that your aspect ratio is quite great in a boundary layer cell, but it's okay because you are not worried about you're not worried about the lateral direction. You're worried about the normal direction only. Okay. So and you shouldn't have a development of grid cell size very suddenly either. So avoid the development of grid cell size like this. 1.2 multiplier is okay, and more than that is not that good. 1.1 is nice. So this is a high aspect ratio one, this is a low aspect. So these are two high aspect ratio grid nodes. And you will see different mesh quality parameters in your simulation. Okay. So it will tell you the number of grid nodes against A quality. Now this is for skewness basically. Okay. And you will see in your simulation, you can check different mesh qualities in your windows. So for example, for a boundary layer, now that is your velocity boundary layer. So to resolve the velocity, you can see that your velocity changes fairly rapidly in here. So you need to catch that rapid change using a boundary layer mesh. Now this mesh will not catch that. Okay, this is inadequate, and this is a good mesh. Okay, but the aspect ratio here is large, but you are not worried about that because velocity changes only in that direction. The different velocities have changed in that direction, not in the longitudinal direction. Okay. So these are a couple of some examples. Now you need to resolve the boundary layer here in this near the car and on this winglet or aerofoil as well. Okay, we'll stop at that, and thank you for listening. So I'll see you here next week.